And here we are. It's the physics video lecture. Physics 190 video lecture 6. Okay, today we have some really great material with the Koshi integral theorem and then the Koshi integral formula. So I'll remind us what we had. In fact, so Koshi, what we ended with, we now have closed integral f of z dz equals 0 if the function is analytic, which means it just has to have one derivative. Okay. So if f is analytic in and on the contour C. Now that starts with, say, this kind of contour. C orientation is always counterclockwise. No reason for that bump there. Okay. But then we had multiply connected domains. So suppose the contour C includes, or the region, suppose the region excludes that inside of that circle there, then we can take this and the circle inside as being part of the oriented contour. Maybe another color would be in order. And in fact, this one would be clockwise. And the way you would deal with that is you come in counterclockwise here. Actually, say to here, go in, go around this thing. Actually, let's do this right. Okay. So we come in here, go in and traverse the inside one clockwise, and then go out on that one. So these two adjacent contours cancel each other, okay, because they're right up against each other. And so this contour C would include this entire thing here. And what we then have, and I did this with 2 of these inside, you do with 1, 2, 3, many, but we'll just do this one right here. So what we can do is we can say this total contour C is the outside C sub 1 and the inside C sub 2. And then we have f of z dz. The total one here is equal to the integral f of z dz c sub 1 f of z dz c sub 2. That's still equal to 0, and therefore the outside one is equal to the negative of the inside one. Okay. And the inside one, what we're going to see in our next theorem, you often just squeeze it down to an infinitesimal little circle. So there's you got to be careful with the orientations. So these two contours include their orientation, and this one here is oriented clockwise. So if I wanted to dispense with that, I could say they both have a proper orientation, and then I would put a minus sign here. Okay, we'll deal with that when we get there. Okay, so just be aware that this clockwise integral has the minus is negative value of the counterclockwise integral. Okay, so I'll leave that right there. So what we want to do, so yeah. Now we want to prove Koshi's integral formula. And then we'll start getting some really great applications. So Koshi's integral formula, actually we could get the applications with this right here, but we'll take it this next step further. Koshi's integral formula is, again, we have, well, this time we have let's go ahead and formulate the thing right away. So yeah, f of z analytic in and on the contour C. And so when I say in, I mean in the inside of this region here. And there's our contour C. So we're really doing something similar to this, but analytic in and on C. Now I'm going to evaluate the integral 1 over 2 pi I integral, closed integral on C of f of z divided by z minus z sub 0 dz. So this whatever function I have divided by this z minus z sub 0, and this is going to be equal to 0 if z sub 0 is outside, and it's going to be equal to f of z sub 0 if z sub 0 is inside. Okay. So what I have here, I could either have my z sub 0 that I'm referring to right here outside that curve, or I could have it inside. We're not going to deal with it exactly on the curve, and it doesn't matter because we could always deform the curve infinitesimally and avoid it. Okay. So analytic in and on C, and we imagine we've got a neighborhood around there, so we're not worried about it. Those are details. Okay. So the proof of this, for the first one here, 1 and 2, is almost self-evident. Okay, if z sub 0 is outside, f of z is analytic. Okay, and 1 over z minus z sub 0, we're just multiplying these two analytic functions. Product is also analytic, differentiable, no problem. You can just literally take derivatives. Okay, derivative of 1 over z minus z sub 0, just the standard derivative. So the proof for z sub 0 outside is that integral f of z minus z sub 0 dz is analytic. The whole thing is analytic, and therefore we get the 0 by the Koshi theorem. Okay. So that one's done. The inside one is a little more interesting, or much more interesting, because if z sub 0 is inside here, then clearly this function, the entire function f of z times z minus z0, is not differentiable at that one point. It's actually differentiable everywhere else, but at that point, it's not differentiable. Okay. So we'll do the second case. And see why this comes out. So this integral here is just equal to the value of the function in the numerator at that point. So this is part 2, proof z inside, z sub 0 inside that region. Then we have to do this construction we had just been practicing. I'll draw a big one. Okay, so we've got this region, we've got our z sub 0, and what we do now is come around on a contour, I'll come and say up to here, go in here, little circle, back out again. Okay. Because now Koshi's theorem tells us that the integral around this entire contour, and I'm going to call it C1, I'll call the outside one C and the inside one, yes, absolutely. This, by the way, is just a C, don't mix that up. C is the outside one, and I'll call the inside one C sub 1. So by the integral theorem that we had, we have 1 over 2 pi I integral outside z minus z0. Let's see, we can do the z's. Yeah. Yeah, okay, so if I'm traversing this thing with these two integrals, then I'm going to put that minus sign in like I was just talking about, 1 over 2 pi I integral f of z, z minus z sub 0, dz both times. This is going to be equal to 0, so let me just put that note there. This is because we're traversing the entire thing and we have an analytic function, 2 pi I, I'm just multiplying by, 2 pi I'm just multiplying by. But the minus sign is because I'm traversing c sub 1 counterclockwise again. Whereas on this path here for the theorem, it would be clockwise all the way through. So I'm just going to write counterclockwise, and that's why I changed the sign. Yeah, so that's better that way, because now I can just equate the integral on the outside, which is the one in the theorem. So 1 over 2 pi I c f of z dz z minus z sub 0. I can just equate that to this one here. 1 over 2 pi I. Let's see if we just get it in this space. C sub 1 f of z, z minus z sub 0. Good, I'm just rewriting this again and again. But now we're going to evaluate this thing. So leave some room under here. We're going to evaluate that for the following situation. Z is equal to z sub 0 plus r e to the I theta. We're just going to turn that into a tiny little circle of radius r. I'll go ahead and put the r there right now. R e to the I theta. And we've done this before. So now we're going a complete circle at 0 to 2 pi. We have f of z naught plus r e to the I theta. And then the dz is I r e to the I theta d theta. What about our denominator? Z minus z0 is r e to the I theta. So we cancel r e to the I theta, r e to the I theta. We can pull I out, okay, and then we're going to take the limit as r goes to 0. So let's just we do need a little more room here. And in fact, we'll have the theorem we'll look at when we're all done to make sure we saw what happened. Okay, so we're continuing this thing and pull the I out, so we have 1 over 2 pi integral 0 to 2 pi f of z 0 plus r e to the I theta d theta. And that'll do the trick. Yeah, the I canceled. Good. Here we go. So this r is just an arbitrary radius of an arbitrarily small circle around that z sub 0 point. So if we take the limit as r goes to 0, we're going to end up with f of z sub 0. But for any small r, this integral is approximated just by 2 pi. Okay, because that's inside the integral now. I'm sorry, that's inside the argument. So this f just tends towards one constant value, and then the d theta evaluated from 0 to 2 pi is going to give us 2 pi. So what we have here, in the limit as r goes to 0, we have f of z 0 and then 2 pi over 2 pi. And there you have it. So that is f of z sub 0. And there's our theorem. We didn't erase it. So 1 over 2 pi, closed contour, f of z divided by z minus z0 dz. If z0 is outside, it's 0. If z0 is inside, it's equal to f of z0. So this kind of integral, we're going to see, we construct these all over the place, replaces some big contour type of thing by the value of the integrand at one point. So I think I'm going to go straight to the application. If I'm not mistaken, that's what's next. Yes, good. So we have the integral formula. We'll even leave it up here at the top. And start evaluating interesting integrals. Yeah, so the example, the integral we want to evaluate, this is one you've seen before, certainly. Integral dx 1 plus x squared from minus infinity to plus infinity. So this is just an integration along the real axis, real numbers, okay? The kind where we learned that we would take, formally we would integrate it from minus r to plus r and then get the limit as r goes to infinity, okay? So we've seen this kind of thing before. Now what we're going to do is rewrite it like this. Dx, this is still along the real axis, but we can write this 1 plus x squared or x squared plus 1 as x plus I times x minus I. Right? Because this is when you've seen before, you have x squared plus ix minus ix, and I times negative I is 1. Okay, so there's a factorization. And if we look at this in the complex plane, then we'll see that there is a pole at z equals I. Okay. In other words, if these were complex numbers, then we would have a pole there, and it would be just like this formula. So let's now consider the integral 1 over z plus I, 1 over z plus I times 1 over z minus I dz. And we're going to let the contour be this one. This picture here. Here's R, here's minus R, here's our semicircular contour. So this is just made for Cauchy's integral formula, okay? Because our f of z is 1 over z plus I, and we're dividing that by z minus z sub 0, so I is equal to z sub 0. Here, f of z is equal to 1 over z plus I, z sub 0 equals I. That's this one. And we can apply Koshi's formula. And integral 1 over z plus I 1 over z minus I along this entire contour here. So the entire contour is the semicircle and the real part is equal to f of z sub 0 times 2 pi I, right? Cross multiply, so that's equal to 2 pi I times f of z sub 0. Z sub 0 is I, so f of z sub 0 is 1 over I plus I, 1 over 2I times 1 over 2I, and what do we get here? Pi. So this integral here is just equal to pi. Now let's relate it to the one we're trying to solve. And I'll actually just state everything that we're going to do before I write it out. What we're going to do is let r go to infinity. Okay. Then this integral here, the entire integral, consists of the one we were looking for, minus infinity to infinity, plus that semicircle. Okay. But the semicircle of this form, that integral, vanishes in the limit as r goes to infinity. We saw that with the proof of, or with the application of the Darboux inequality. So we actually already have the answer. The answer is this integral from minus infinity to plus infinity is equal to pi. I'm just going to write that out and make sure all the steps are there. And then I'll put a couple problems of a similar nature up on the board for you guys to solve. So at this point I can erase this. So I'll write this in this order here. So we have pi, that was what we found, was equal to 1 over z plus I, 1 over z minus I, dz along this path. And that is equal to, so this integral is equal to minus r to capital R dx 1 plus x squared. Because that's the part that is along the real axis, okay? And then it's plus this integral dz 1 plus z squared, right? I don't have to always write it as that factorization. This is what it was originally, along what I'm going to call c sub r, which is that semicircle up there. Okay. Now what we do is take the limit as r goes to infinity, and then we get the one we're looking for, plus infinity dx 1 plus x squared, plus something that vanishes. And this thing is, well, something that vanishes. Plus 0. I'll just write plus 0, comma, because integral of this thing here. This is the one this is almost the one we did in our notes. In fact, we did z squared, dz over z squared. Is that the one we did? dz over z squared is equal to 0. Close. We may have done this one in our Darboux proof, but we'll do it right now. Yeah. So this one is 0 to pi z, let's go ahead and write this, z equals r e to the I theta, dz equals I r e to the I theta d theta. We've done this one a couple times, nothing wrong. So I r e to the I theta d theta. And what we're going to do is estimate this thing. And 1 plus z squared is less than the integral. Yeah. So we've got an inequality r squared e to the I 2 theta. We've already got an inequality here. I e to the I theta, e to the I 2 theta, these are all ones, and so we ended up with equals I over r goes to 0 as r goes to infinity. So this by the way, is the Darboux inequality again, which is really just saying that the length times the maximum value of the integrand, okay, is what you estimate this with. So this semicircular integral goes to 0, and we're always going to want it to go to 0 in these applications here. Good, but there's what we needed. This one vanishes in the limit as r goes to infinity, leaving us with the integral we set out to evaluate, equal to pi. Okay, let me consult with the clock here. Good. So now I'm going to set up a couple of problems, and that'll give us a chance to discuss what we've done so far. There's a whole class of integrals that we can now evaluate according to this technique. And that's what I'll talk about next, and put a couple there on the board for you guys to do. And then we'll also see the limitation of it. We have to keep going with the theory in order to get a bigger class of integrals. So I think advantages by Darboux. So I'll call these homework problems. And there's just two integrals of this type, and we can kind of start doing them together. So we're looking for minus infinity to plus infinity dx x squared plus 1 times x squared plus 4. Okay. And the second one here is basing it on the same integral. I'll put x squared plus 3 in the numerator, x squared plus 1 times x squared plus 4, dx, and dx. Okay, question mark, homework. These are what we want to evaluate. And if you look at the structure of what we just did, you see that we have these same poles in the denominator, except more of them. And we really want to do the same thing we did right there. So since these both have the same pole in the denominator, I'm going to just draw one big picture here. X and Y. See, this factor, this can be factored to x plus I, x minus I, x plus 2I times x minus 2I. And the same thing down here, x plus I, x minus I, x plus 2I, x minus 2I. And again, we're going on the real axis. These are real integrals, but we have a pole here at I and at 2I. Okay. Yeah, I said it. I don't have to write that down, okay? Because it's actually still on the board. up here. X plus I, X minus I, times X plus 2I, X minus 2I. So how are we going to use Koshi's theorem integral formula? Let's go out to R and minus R here. There we go. Well, this semicircular portion of the integration has to vanish in the limit as R goes to infinity. And we'll see it's no problem here. We have x squared, x squared, x squared. So we have x to the fourth in the denominator, x squared in the numerator. So we have 1 over x squared. You have to have at least 1 over x squared. Well, not quite, but let's just say that makes this one vanish as, 1 over r. You could have weaker dependence, but we'll just talk about that one. And this one we have actually 4 powers of r of x in the denominator. So this one will certainly converge. Okay, so both of these are going to vanish here. And so we'll be replacing this integration with this following one. Coming into here, going up, got a semicircle, up, another one, down, and down. Okay. So the Koshi integral theorem gives us a 0 for this entire curve here, including these clockwise portions. Okay. The one we want is this limit goes out to r plus minus infinity. There we go, minus r. So these two individual ones are obtained by Koshi's integral formula. So it's essentially being evaluated twice here, once at each pole, the same calculation we did up there. This outside one vanishes by Darboux, and what we're left with is the answer, okay, is the one along the real axis. So with this technique, it could just get more and more tedious, but you could construct a great number of integrals of this type. As long as you have 2 powers of x more in the denominator than you have in the numerator. Okay, so I and 2i. So that's how you do those. Good, that's a good start. Now we have enough time, although I want to not go too long. Here's what I'll do. I'll formulate a problem that we can't quite solve with this technique, and then we'll get to it next time. In other words, we need some slightly more powerful estimates to do a whole other class of integrals, and the class I'm going to do is example here next time, but we can talk about it already. So a little more room here. So this integral e to the, what do I have here? Cosine of ax over 1 plus x squared dx. And here's the thing, and this would be from 0 to infinity. Okay. That looks like a nicely posed problem, and in fact it seems like we would get the same estimate because the cosine is very bounded, right? However, cosine in the complex plane, so you want to go up here with the cosine, you're going to find that it's actually the difference of exponentials, okay? And they're not just getting small up here. So for that reason, we need another theorem called Jordan's lemma that will give us a way to estimate these kinds of integrals and do these. But then you can see it's going to open up a whole other type class of integrations. I think what I'll assign is this one from, I'm going to assign that one, but we can't quite do it with just this simple technique, even though we just have it seems like we just have the pole here at x equals I. this is the complex x. This is z when we go around here. Okay, I think that's a good place to stop. So we can talk about problems of this type next time and go a little deeper and add another class of functions where we can do these amazing integrations where we just, what you'll see, you're just picking off the value of a function at two places here, and that replaces this infinite integral. Okay, so yeah, this subject just keeps getting better and better, and we'll see you next time.